Okay, so this is section 16.2b. We're going to continue with the idea of a line integral. And in this particular section, we're going to extend the line integral to not just being able to evaluate line integrals over functions, but also over vector fields. So in order to do that, this first video is pretty much going to be developing the theory and giving us somewhat of a more usable formula, something that's more common to what we do in calculus as far as the actual formula is concerned. It'll be the same general idea, but it's just going to be developing the formula. And we might do one example, not sure if we'll have time. If not, we'll come back and do all the examples in the second video. This will be a 2-video lesson. Okay, so in order to do this, some of the theory, we need to recall some things here. R of t is your position vector. X of t, y of t, z of t if we're in 3 dimensions. Basically, the idea is that R of t is a vector which comes from the origin and goes out to some point in space. If you put all of the R of t's together for a specific thing, then you're going to basically fit the space curve. You're going to form whatever the curve is. R prime of t as a derivative would basically be the derivative of R of t, or the tangent vector that's formed off of each individual position vector. And it literally is just taking the derivative of each piece. The magnitude of R prime of t is the square root of each one of the derivatives squared added together. And that really is just the length of the vector that is the tangent vector that's formed by R prime of t. So it's that length of that vector. It's the magnitude of it. And then number 2 here, t of t, capital T of t, is your unit tangent vector. I'll actually write that here. That's the unit tangent vector, which just means you take your tangent vector, R prime of t, and divide it by its magnitude, and you're going to get a tangent vector of length 1. And then we go back to a formula that we used way back when we first started, that the dot product of 2 vectors a and b is the same thing as the magnitude a times the magnitude of b times the cosine of the angle in between. Okay, so we used that a really long time ago when we started talking about dot product properties. All right, so we're going to use all these things in the development. So let's go ahead and take a look. What we're going to create here on this, basically the first quadrant of a XY type plane, we're basically going to create kind of a map. So this will be north, that'll be east. What we've got, we've got some kind of a vector field that's going to be created basically like wind velocity. So we'll say that f of xy is going to be the vector field which creates the wind velocity. And our wind is going to be doing something like this. You know, depending on where you're at, the length of these things might be different. Okay, there is actually no rhyme or reason to the way I'm doing this. I'm just trying to create things of different lengths along this particular portion of the vector field. And what we'll say is maybe these are 2 streets. So maybe our house was right here at the corner. This will be our house. Door with a knob, upper window, all that kind of stuff. There's the top of our house. There's our house. So maybe we live on the corner of what's pretty popular, Elm Street. So maybe we're in Freddy Krueger's house. I don't know. And what's another very popular street? Fern, no. Oh, Main Street. Everybody has a Main Street. So we'll put Main Street over here. I'm trying to anyway. Main Street. Anyway, so we've got our vector field, and the wind is blowing, it looks like, pretty much due east. So the idea is, maybe we're going out for a walk through our neighborhood, and I start at my house, and I kind of follow this pattern right here, and then I'm going to come up here, and then I go over this way, and then maybe this is the path that it takes or whatever, and then I finish up here. And maybe it's a friend's house or something up there. I'm not going to draw another house. So the idea is, when I am going along my path, like let's say that I'm going to look at the region maybe from here to there. Okay, each place along that region, I'm going to have a tangent vector from my position. And it's going to be different depending on where I am. And what you should be able to see is that obviously the tangent vector is going to be based upon your position. But the real question comes up is, does the vector field help or hurt along the path? Or maybe neither. So does the vector field help or hurt along the path? And then if it does either help or hurt, so if so, how much? So those are kind of the two questions that we're going to have. So what does that really come down to as far as mathematics and physics and stuff like that is concerned? Well, here's the real question that we're going to ask. Those other two questions are kind of basing it towards this, but here's the real question. How much work does the vector field do to aid you to the end of the curve? So how much work does the vector field do to aid along our path to the end of the curve? That's kind of the real question there. So how are we going to determine that? Well, we have our path, which is maybe defined this way. And we have a force which is acting on ours, which is coming out this direction. So we'll call this our wind, which is our force vector. There is an angle which is created in between our, it's supposed to be in green, in between our path and the force vector. Well, along that path we have a tangent vector. Whatever exactly that looks like, I'm not sure. It's going to look very similar here, but so again, we'll say that this, I keep picking the wrong colors, sorry. So we'll say that this right here is our force. Okay, whatever the tangent is, it may not be exactly the same angle that I just drew there. Maybe it looks a little steeper. Who knows how the tangent vector is going to look here. But we'll say that, this is our tangent vector. Tangent vector has two components to it. It's got the component which is parallel to it, so pretty much in the exact same way. And then it's also got the component which is perpendicular. And the perpendicular is going to hit the end of your force vector like this. And again, that stuff goes way back. That is the perpendicular part of your tangent vector. And then you, of course, you have your parallel part, which is along the red line. The force is basically the sum of the two components. It's the component of force, which is parallel to the tangent vector, plus the component of force, which is perpendicular to the tangent vector. Well, the part that's perpendicular to the tangent vector actually does nothing. It has no meaning. And that's because if it's perpendicular, it's not helping you, but it's not hurting you either. So this piece right here means nothing. Okay, it does not help, does not hurt. Basically, it would zero itself out, because if it's perpendicular, it's not aiding you, but it's not hurting you either. So it's going to zero itself out. This piece, however, which is parallel to the tangent vector, obviously is the piece that's going to help. Because if it is going in the same direction that we are moving, then it's going to help. So this is the only piece that will help. Okay, I hope that that makes sense. Let's go ahead and extend this idea now to develop our formula. That's why there's kind of a completely blank page in the next page here. So again, we've got our force, which is going in this direction. We've got our tangent vector, which is going that way. And then, of course, we have the perpendicular part. Oops, that is supposed to be a different color. It's really being too sensitive here, or not sensitive enough, I guess. Okay, so there's our perpendicular, which again doesn't do anything for us, but we do have an angle in between. Call that theta. So this is what we know. We know that cosine of that angle is the adjacent over the hypotenuse. Well, we're going to call this adjacent side. Let's use orange. We're going to call this adjacent side here h. Well, it is technically t over t. I'm sorry, t of t. We're just going to call it h. So the cosine is going to be h over the magnitude of f. It doesn't need to be the magnitude, because remember, f itself is a force. We need the distance, or we need the length of that force. So we need the magnitude, because we are talking about the lengths of the sides of a triangle. So we know that if we want to solve that for h, we would just multiply both sides by the magnitude of force. All right, so stick with me on this next line here, because you might think, well, where the heck did this come from? Well, somebody had to think of it, obviously, and that's where it came from. So if we were to take, remember the formula that we used, I guess it was number 3 on the first page, was that the dot product of two vectors. So if I was to take t of t and dot it with the force vector, so I'm taking the tangent vector, unit tangent vector, and dotting it with the force vector. Well, that would be the same thing as magnitude of the unit tangent vector, magnitude of the force, cosine of the angle in between. Well, we've defined this already. That's h from the line above. And the magnitude of the unit tangent vector, well, it's a unit tangent vector, so the magnitude is 1. And that is h. Let me make that a 1 and not look like an I. So that's 1, and that's h. So ultimately what we get here is that the dot product of the unit tangent vector with the force is the magnitude of force, cosine theta, which is h. So ultimately what we want to do, in order to figure out how much this force is helping us, is to add up all of the h's. So we want to add all of the h's. Since h is that it's the dot product of the force and the unit tangent vector. So that's the stuff that's in the direction of the tangent vector. It's parallel to the tangent vector. Well, that's going to create a line integral for us. So we would take the line integral over c of the force dotted with the unit tangent vector ds per arc length. So we can rewrite that. The line integral, the force dotted with the unit tangent vector, and then the ds part we know is, and I guess we're assuming this is two-dimensional right now, this is the square root of dx dt squared plus dy dt squared dt. But what is this? Well, according to what we said on the previous, or on the first page, that's just magnitude of r prime of t. Right? Because that's what that is. The dx dt and the dy dt is really just the r prime of t. And then when you take the magnitude, you take those, the r prime components, square them, take the square root. That's what that is. And the unit tangent vector is defined to be r prime of t over the magnitude of r prime of t. If we are multiplying these two things together algebraically, we should see that those magnitudes are going to cancel themselves out. I'll write it out in one more step, but hopefully that should be something you can see. So we have the line integral f dotted with r prime of t over the magnitude of r prime of t times magnitude r prime of t dt. So, oops, forgot the extra, there we go, extra bar there. So the magnitudes are going to cancel out, which simply leaves us with the integral over c, line integral, of f dotted with r prime of t dt. But r prime of t dt is the same thing as dr. If you think about it, that should make sense. Here, I'll put this over to the side, that dr over dt is the same thing as r prime of t. So if you multiply the dt to the right side, you get that dr equals r prime of t dt. So ultimately, our formula for line integrals is going to be the line integral of f dot dr. Biggest thing here is to remember what these things mean. You've got to remember that dr is r prime of t dt, and that r prime of t is your derivative. So that's all that it is. It's the derivative of the parametrically defined r function. So when we do this, the function, or the force, f, has to be parametrically defined. R prime is just going to be the derivative of that dt. So your dr is really just that derivative. Okay, I think this is where we will stop the first video. This is the important formula right here. You can memorize it as the line integral of f dot dr, or you can memorize it as the integral of f dot r prime of t dt. It's exactly the same thing. The r prime of t dt tends to make more sense to people, but we've just shortened it mathematically to dr. So we will come back and we will do the rest of the examples in the second video.